Learning outcomes. After studying this module, you shall be able to know about formation and stability of inorganic complexes in solutions, optical methods for obtaining the stoichiometry of complex, that is determination of the composition of complexes. You will also learn about Job's method. Yes, it is rightly pronounced as Job's method and not Job's method, and also the limitations of Job's method. Let us begin with the introduction to this module. The optical properties of complexes are governed by the formation of coordinate bonds between ligands and metal ions. The complexation in solution can easily be detected by various analytical instruments, for example, via UV visible spectrophotometer, fluorimeter, etc., even at very low concentrations. The basic conditions laid by the Lambert-Beer law should be obeyed for selective determination of any species in solution. With this, now let us understand what are binding constants. The binding constants, which are also known as association constants, these are a type of equilibrium constant, that is capital K. It is associated with the binding reaction between metal M and ligand A molecules. So, we have M plus A giving us the complex Ma. Now, at the equilibrium, binding constant for the forward reaction and dissociation constant for the backward reaction, they are given by the equation, that is rate of forward reaction is equal to rate of the backward reaction at equilibrium. So, we have the binding constant for forward reaction, that is association constant Kf, and the dissociation constant for the backward reaction as Kb. So, at equilibrium we have Kf into concentration of metal ion into concentration of ligand is equal to Kb into concentration of complex. The overall constant of the reaction is referred to as binding constant and is represented as K subscript A, which is equal to Kf upon Kb. On substituting the values of the expression Kf upon Kb from the previous equation, we get Ka as concentration of the complex upon in denominator product of concentration of metal ion and concentration of ligand. Over here we are using the term concentration, but it is important to remember that equilibrium constant or binding constant over here is a unitless quantity. Ideally, the best term to use is activity, which is expressed as product of activity coefficient into concentration, and for very dilute solutions the activity coefficient tends to 0 and therefore, the activity becomes equal to concentration. So, numerically the value remains as that of the concentration term, however, it becomes unitless. For the sake of simplicity, we are using the term concentration throughout so that it becomes easy for the learner to understand. Now, with this introduction to binding constant, let us now move to the methods which are used for obtaining the stoichiometry of a complex. For example, if we have a complex getting formed between metal ion and ligand as N into A plus M into capital M, giving M of M into A of N, that is M subscript M, A subscript N. Now, there are three common optical methods for determination of composition of complexes. Number 1, continuous variation method or Job's method, which we will study in this module. This method is based on the measurement of absorption of a series of solutions in which the molar concentrations of two reactants vary, but their sum remains constant. Second method under this category is mole ratio method. This method is based on the measurement of absorption of a series of solutions in which the analytical concentration of one reactant is held constant while the other is varied. And the third method is slope ratio method. In this method, the reaction can be forced to completion with a large excess of either metal or ligand. This method is specifically used for studying weak complexes. Now, let us begin with continuous variation method. Let us try and understand what this method is all about and how we can use this method to determine the stoichiometry or composition of the complex under consideration. Job's method. This method is also known as method of continuous variation. The principle of this method is that the mole ratio of the metal ion and the ligand is varied between 0 and 1 at constant total concentration, that is total concentration C is equals to Cl plus Cm, where L refers to ligand and M refers to metal ion, and the absorbance of the solutions of different composition is measured. Now, the absorbance is then plotted against mole fraction of the ligand, that is chi L. If only one complex species has been formed with composition Ml subscript n and the absorbance is measured at a wavelength where neither the metal ion nor the ligand but only the complex absorbs, then n, that is the average number of ligands bound to one metal ion, can be calculated from the maximum obtained in the curve. So, then the factor n, that is the average number of ligands bound to one metal ion, can be calculated from the curve numerically or mathematically as n is equal to, in numerator we have mole fraction corresponding to maximum of the curve upon in denominator 1 minus maximum mole fraction, or rather one should say 1 minus mole fraction corresponding to maximum in the curve. This is a very common method for determination of composition of complexes. Equimolar mixture of metal and ligand are taken and are mixed to give a series of solutions having the same total concentration of metal and ligand, but varying the concentration of metal and ligand individually. As you can see on your screen, a table where such set of solutions are prepared, for which we observe that the total concentration of metal and ligand remains constant. However, we are varying the concentration of metal and ligand individually in the solution. So, if you have a look on your screen, you will find that we take initially metal as 10 and ligand as 0 and the total concentration remains 10. Similarly, we vary this as 9 1, 8 2, 7 3, 6 4, 5 5, 4 6, 3 7, 2 8, 1 9 and 0 10. In all the cases what we observe that total concentration remains the same. So, if we consider a complex reaction of the form M plus N into A giving MAN, that is MAN is my complex and A refers to ligand and M refers to my metal ion, then K becomes equal to complex concentration in numerator upon in denominator product of concentration of metal ion into concentration of ligand raised to the power of numerical coefficient. Suppose chi is the mole fraction of ligand and 1 minus chi is the mole fraction of metal present in the solution, that is the free metal ion mole fraction. The total number of moles of reactants present in solution at equilibrium, if represented by capital N, that is the number of moles of metal plus the number of moles of ligand in 1 liter of solution, then we assume that the concentration M represents the free metal ion concentration, concentration L represents the free ligand concentration in the solution, and with this we can then obtain the concentration of complex in the following manner. So, the free metal ion concentration can then be equated as Tm minus concentration of the complex, where Tm represents the total metal ion concentration. So, I can represent the free metal ion concentration further as 1 minus chi into n minus concentration of the complex, where I have expressed the total metal ion concentration as 1 minus chi, that is the mole fraction of free metal ions, into capital N, which is the number of moles of metal and ligand present in 1 liter of the solution. Likewise, we can represent the concentration of free ligand as Ta minus N into complex concentration. Over here, N is the coefficient corresponding to the ligand, that is the number of ligands that result in complex formation. Further, since we have assumed that the ligand mole fraction is chi, we can further rewrite this equation as chi into capital N minus N into complex concentration. Now, if we differentiate this with respect to chi and apply the condition of maximum for this equilibrium reaction, so if we apply this condition, we obtain the following expressions: d of complex concentration upon d chi is equals to 0 at the maximum. For metal ion, since we have taken the metal ion concentration as 1 minus chi into capital N, on differentiating this with respect to chi, we obtain the expression as minus N. Likewise, the expression for d concentration ligand upon d chi becomes equal to N, capital N. So, what we can write is d of d chi for product of concentration of metal into that of ligand raised to the power n is equal to 0 at the maximum. On simplifying this equation using product rule, we obtain the expression concentration of metal into d concentration of ligand raised to the power n upon d chi plus concentration of ligand raised to the power n into d concentration of metal upon d chi is equals to 0. So, this on further simplification gives us the expression n into concentration of metal into concentration of ligand raised to the power n minus 1 d concentration of ligand upon d chi plus concentration of ligand raised to the power n d concentration of metal upon d chi is equals to 0. Now, if we substitute the expressions over here for d concentration metal upon d chi and d concentration of ligand upon d chi from our previous derivation, where we have taken d concentration of metal upon d chi at maximum equal to minus capital N, and similarly for the ligand it is capital N only. With this, we obtain the expression as concentration of ligand raised to the power n into minus n plus n into concentration of metal into concentration of ligand raised to the power n minus 1 into capital N is equals to 0. This on simplification gives us the expression capital N into concentration of metal into concentration of ligand raised to the power n minus 1 minus concentration of ligand raised to the power n within the brackets. So, we further obtain or simplify the expression as minus n into concentration of ligand raised to the power n is equal to minus small n into capital N into concentration of metal into concentration of ligand raised to the power n minus 1. So, if we cancel out the common terms, we obtain the expression for ligand concentration as n into concentration of metal. Now, if we substitute the values of concentration of metal and ligand, that is free metal ion and free ligand from our previous equations, over here we obtain the expression as chi into capital N minus n into complex concentration is equal to n into 1 minus x into capital N minus complex concentration. This further simplifies to chi into capital N minus n into complex concentration is equal to n into 1 minus chi into chi minus n into complex concentration. This on further simplification gives us the expression chi into n minus n into complex concentration is equal to small n into capital N minus small n into capital N into chi minus small n into concentration of complex. Further simplification gives us the expression chi into capital N plus small n into capital N into chi is equal to small n into capital N plus small n into complex concentration minus n into complex concentration. Cancelling the common terms gives us the expression capital N into small n into 1 minus chi is equals to chi into capital N. So, from here we obtain the expression for n, that is the average number of ligands per metal ion, as chi upon 1 minus chi. This is the same expression that we stated few minutes back. So, on plotting the graph between absorbance of prepared series of solutions and their corresponding mole fractions, the exact ratio of metal and ligand at equilibrium can be observed at maxima of the graph. For all the cases of graphs that will be shown now on your screen, do consider the absorbance on y axis and mole fraction on x axis. So, let us see the first case where we have a 1:1 metal is to ligand complex. As you can see from the graph, the maximum lies around 0.5, that is for 1:1 we have n as 5 upon 5 or 0.5 upon 0.5, which is 1. So, for 1:1 complex we observe the maximum at 0.5 mole fraction of ligand. So, with this we can conclude that the average number of ligands per metal ion is equals to 1, because n is then obtained as 0.5 upon 1 minus 0.5, which is 0.5. So, we have 0.5 upon 0.5, which is 1. Similarly, the second case is where we have a 1:2 complex formation, that is 1 metal ion for 2 ligands. So, it is a bidentate ligand then. So, as you can see from the graph, the position of the maximum, and from here we obtain n factor as 2. Likewise, the third case is where we have a 1:3 metal is to ligand ratio, and again from the maximum observed in the graph we obtain n as 3. Now, let us consider the very first case of 1:1 complex. So, at maximum the chi factor is 0.5 for the ligand and it is 0.5 for the metal as well. So, the total mole fraction is 1. So, we say that it is 1:1 complex. For 1:2 complex, chi is obtained as 0.67 and substituting this chi value gives us the n value as 2. So, from there we say that it is a 1:2 complex. Likewise, for the third graph, that is 1:3 complex ratio, we obtain chi as 0.65, and when we substitute this chi in the n expression, we obtain the n value as 3, and from there we say that it is a 1:3 complex. Now, for strong ionic compounds, pH should be maintained during the measurement of spectra. Job's method is also used for calculating approximate value of stability constant. From the degree of formation of complex, the value of free metal and free ligand are calculated, and from there stability constant of the complex can be calculated. Let us see how we can use Job's method for determination of beta, that is the stability constant. Let us assume that at absorbance Am, the whole complex has been formed and the whole metal is consumed. So, we can write the expression as A upon Am is equals to complex concentration upon total metal ion concentration Tm. Now, we know that we have expressed the free metal ion concentration capital M is equals to Tm minus complex concentration. So, at Am, the free metal ion concentration becomes 0 and Tm becomes equals to complex concentration. So, what we obtain is complex concentration at Am as Tm into A divided by Am. On substituting this metal ion concentration in the stability constant equation, that is K is equals to concentration of complex upon product of concentration of metal into that of ligand raised to the power n, we obtain the expression as A upon Am into Tm divided by concentration of metal into concentration of ligand raised to the power n. Now, on substituting the concentration of free metal ion and free ligand in this expression, we obtain K as A upon Am into Tm in numerator divided by in denominator Tm minus concentration of complex into Ta minus n into concentration of complex whole raised to the power n. This on simplification gives us the expression K as A upon Am into Tm in numerator divided by Tm minus A upon Am into Tm into Ta minus n into A upon Am into Tm raised to the power n. This gives us the expression on simplification as A upon Am into Tm divided by Tm into 1 minus A upon Am into Ta minus n into A upon Am into Tm whole raised to the power n. So, with this on further simplification, we obtain the expression for K as A into Am raised to the power n in numerator divided by Am minus A into Am Ta minus n into A into Tm whole raised to the power n. Hence, we can say that by knowing the values of A, Am, n, Tm and Ta, the value of stability constant K can be calculated. The greater the stability of the complex, the sharper is the peak of the curve and the greater is the error caused by incorrect reading of the ordinate values. On the other hand, if the stability of the complex is small, the curve becomes flat and the drawing of the tangents becomes uncertain. The Job's method is the most commonly used method due to simplicity and rapidity of this process. Its applicability, however, is limited. Now, let us look at the limitations of this method. This method is applicable to only one type of equilibria, that is only one type of complex formation in the solution. This is applicable to moderately stable complexes. It means it cannot be applied to very weak complexes. And if the complexes are colorless, then spectrophotometric method cannot be used. Measuring the absorbance of prepared series of solutions according to Lambert-Beer's law is another limitation to this process. Also, pH and ionic strength must be maintained throughout the process as constant values. Let us now summarize what all we have learned in this module. The binding constant, which is also referred to as association constant, is a type of equilibrium constant. Continuous variation method, that is Job's method, mole ratio method and slope ratio method are the common methods for obtaining the stoichiometry of the complex. Over here, we took up Job's method in detail and we found that Job's method is a method based on the measurement of absorption of a series of solutions in which molar concentrations of two reactants vary, but their sum remains constant.